You ever stop to think about infinity? I mean, really think about it.
It's one of those concepts that just kind of breaks your brain a little, doesn't it?
Totally. And specifically, this idea of whether all infinities are actually, well, the same size. It sounds like a riddle.
It really does. Infinity should just be infinity, you'd think. But yeah, that's what we're diving into today.
This difference between countable and uncountable sets.
Exactly. That gets right to the heart of it, this idea that some infinities are, believe it or not, bigger than others.
Okay, countable, uncountable. Sounds straightforward, maybe.
Yeah.
One you can count, one you can't. But with infinity, how does that even work?
Well, think of it like this. A set is countable if you can basically pair up each thing in the set with a unique natural number.
Like assign 1 to the first thing, 2 to the second, 3 to the third, and so on.
Precisely. You can list them, even if that list goes on forever. You're essentially counting them one after another.
Okay, so what counts as countable then? Give me some examples.
Well, the most obvious one is the set of natural numbers itself, 1, 2, 3. Each number just matches its position in the count.
Right. That
Yeah.
makes sense.
But here's where it gets interesting. The set of all integers, so including 0 and all the negative number.
Wait, -1, -2 going out forever in that direction too?
Yes.
How can you possibly count all of those?
There's a clever trick. You can order them in a specific way. Start with 0, then 1, then -1, then 2, then -2, then 3, then -3.
Oh, you alternate positive and negative moving outwards.
Exactly. And if you do that, you can see that every single integer, positive or negative, will eventually appear in that sequence. You can assign a natural number count to each one's position.
Huh. That's pretty neat. Okay, integers are countable, but what about fractions? Rational numbers.
Good question. That feels like it has to be bigger, right?
Yeah, because between any two whole numbers, there are infinitely many fractions. Surely that's uncountable.
It really feels like it should be. But counterintuitively, perhaps, the rational numbers are also countable.
No way.
Imagine setting up a kind of infinite grid. Let the rows be the numerators, 1, 2, 3, and so on. And the columns are the denominators, 1, 2, 3.
Okay, so you have like 11, 12, 13 in the first row,
Yeah.
21, 22, 23 in the second.
Exactly. Now, you can trace a path through this grid. Start at 11, then go to 12, then 21, then 31, then 22, then 13. Kind of a zigzag pattern.
A diagonal-ish path.
Yeah, a zigzag or diagonal path that sweeps across the grid. As you go, you just count each unique fraction you hit. You skip ones you've already counted, like 22 is the same as 11.
And that path eventually hits every possible fraction.
It does. It guarantees that every single rational number, P over Q, will eventually get included in your count. So, countable.
Wow. Okay, my intuition was way off there. Naturals, integers, and fractions, all countable infinity. So
Okay.
what's left? What's this bigger infinity?
That brings us to the real numbers. The set of real numbers usually written as R.
Which includes?
Everything. All the rational numbers we just talked about, plus all the irrational numbers.
Like
Yeah,
the square root of 2, those decimals that go on forever without repeating.
exactly those. And that set, the set of real numbers, turns out to be uncountable. It's a fundamentally larger kind of infinity.
Okay, that's our mission then. To really understand why. Why is this infinity of real numbers somehow bigger, more infinite than the infinity of integers or fractions? And I heard something about diagonals.
You heard right. We need to talk about George Cantor and his diagonal argument. It's a brilliant, really elegant proof that shows exactly this.
Cantor. Okay, lead the way. How did he tackle this?
So George Cantor, working in the late 1800s, was doing absolutely groundbreaking work on set theory, figuring out how to compare the sizes of infinite sets.
A real pioneer then.
Absolutely. And one of his biggest results was proving that the real numbers aren't countable. He actually showed that even just the real numbers between 0 and 1 are uncountable.
Just that tiny little slice of the number line between 0 and 1.
Even that slice contains an uncountable infinity, and he proved it using something called proof by contradiction.
Right. That's where you assume the opposite of what you want to prove.
And then show that assumption leads to some kind of logical impossibility. Exactly. So it forces you to conclude your original assumption was wrong.
Okay, so what did Cantor assume?
He said, let's assume, just for the sake of argument, that you can make a complete list of every single real number between 0 and 1.
An infinitely long list, but it supposedly has all of them. Like
Okay, 0 point something, something, something.
0 point something else, and so on, forever.
Precisely. Imagine that list written out, with all the infinite decimal expansions. Now, Cantor came up with this ingenious way to construct a new real number, also between 0 and 1, that is guaranteed not to be anywhere on that list you just made.
How? Using the diagonal thing.
Exactly. You look down the diagonal of your list. So you take the first decimal digit of the first number on the list,
Yeah.
then the second decimal digit of the second number,
Got it.
then the third digit and the third number, and so on, all the way down this infinite diagonal.
So you're picking out this specific sequence of digits from the list. What do you do with them?
You use those diagonal digits to build your new number. Let's call the new number x. To get the first decimal digit of x, you look at that first diagonal digit, the first digit of the first number. You then choose a different digit for x.
How different? Like add one to it.
A simple rule works. The text suggested if the diagonal digit is, say, 5, make the digit for x a 6. If the diagonal digit is anything else, make the digit for x a 5. The key is just making it different.
Okay, so the first digit of x is definitely not the same as the first digit of the first number on the list.
Right. Now you do the same for the second digit. Look at the second digit of the second number on the list. Use your rule, if it's 5, make it 6, otherwise make it 5, to pick the second digit of x.
So the second digit of x is different from the second digit of the second number.
Exactly. And you continue this process forever. The third digit of x is different from the third digit of the third number, the fourth from the fourth, and so on.
So this new number, x, it's 0 point something something.
It's definitely a real number between 0 and 1.
But wait, it can't be the first number on the list because it differs in the first decimal place.
Correct.
And it can't be the second number because it differs in the second place.
Right.
And it can't be the nth number on the list because by construction, it differs in the nth decimal place.
You've got it. This number x, which is definitely a real number between 0 and 1, cannot be any number on the list we started with.
But we started by assuming the list contained all real numbers between 0 and 1.
And that's the contradiction. Our assumption led us to construct a number that should be on the list, but cannot be on the list. Therefore, the initial assumption must be false.
You can't make a complete list of all real numbers between 0 and 1.
It's impossible. The set is uncountable. It's a bigger infinity than the natural numbers you'd use for listing.
Okay, but what if? I mean, couldn't you just take that new number, x, and just add it to your list? Maybe put it at the beginning?
Great question. But think about it. If you add x to the list, you just have a new, slightly longer, infinite list.
Right.
You can just apply the exact same diagonal argument to this new list. Look down the new diagonal, construct a new number using the same change the digit rule.
And that new number won't be on the new list either.
Exactly. No matter how many numbers you try to add, the diagonal method will always generate another real number between 0 and 1 that you've missed. The list can never, ever be complete.
Wow, that's genuinely mind-bending. It's like an unpluggable hole.
It really is a powerful demonstration. So we have this fundamental split, countable infinity, like the integers are rational.
But you can line up and count, even if it takes forever.
Right. And uncountable infinity, like the real numbers, which are so numerous, so dense, you can't even make a list to start counting them.
It still feels a bit weird, though. Like, infinity is infinity, right? Numbers are just abstract concepts.
Yeah.
How can one abstract concept be bigger?
That's a totally understandable intuition, maybe even a philosophical point. But within the framework of mathematics, using the standard axioms of set theory that mathematicians work with, this difference in size, this uncountability of the reals, is a rigorously proven property.
So the rules of the game say they're different sizes.
Yes. Think of it like two infinite libraries. Library A has every book labeled with a unique natural number. Book 1, Book 2, Book 3. You could, in theory, find any book if you knew its number. That's countable.
Okay.
Library B also has infinitely many books, but they resist labeling. Any system you devise to assign a natural number to each book will inevitably miss infinitely many books. You just can't create that one-to-one mapping. That's the uncountable library of real numbers.
That's a good analogy. The size isn't physical space. It's about whether you can make that complete index.
Precisely. It's about the possibility or impossibility of creating what mathematicians call a bijection, a perfect pairing. The reals resist enumeration. The source also used this idea of digital versus analog.
Right, the clock analogy. How did that work?
Think of countable sets, like natural numbers, as being digital or discrete, like digital clock ticking, 1 second, 2 seconds, 3 seconds. There are distinct jumps between values.
Okay, separate steps.
Whereas uncountable sets, like the real numbers, are analog or continuous, Think of the smooth sweep of the second hand on an analog clock. It moves through every single possible point on the dial. There are no gaps, no junks.
Ah, between any two moments in time the hand passes through, there's another moment it also passed through.
Exactly, it's continuous. Which leads beautifully into another really helpful analogy.
Let me guess. The staircase and the slide.
You got it. This one really helps visualize the difference. Imagine an infinitely long staircase.
Okay, steps going up forever.
Each step represents a natural number. Step
Yeah.
1, step 2, step 3. It's discrete. You land on one step, then the next. There are gaps between them, right? No step 2.5.
Right, distinct, countable steps.
Now, right next to it, picture a perfectly smooth slide also going on infinitely. No steps at all, just a continuous, unbroken surface.
Like the analog clock hand's path, but stretched out.
Exactly. On that slide, between any 2 points, no matter how ridiculously close they are, you can always find another point. It's dense, continuous. There's no concept of the next point after a given point.
Okay, got the staircase, got the slide.
Now, try to match them up. Try to put a label from a stair step onto every single point on that slide.
You can't, because the slide is smooth and the stairs have gaps. You label points corresponding to step 1, step 2, step 3. But what about all the infinite points between where step 1 and step 2 would land on the slide?
Precisely. You'll always have infinitely many points on the slide left over, unlabeled by any step. It perfectly shows why you can't make that one-to-one correspondence between the countable naturals, stairs, and the uncountable reals slided. The density makes it impossible.
That makes so much sense visually. The staircase just can't cover the slide completely.
It can't.
Yeah.
And this density, this uncountability of the reals, is intimately tied to another fascinating type of number: transcendental numbers.
Transcendental. Okay, that sounds important. And maybe a little mysterious.
They kind of are. So first, let's talk about what they aren't. There's a big group of numbers called algebraic numbers.
Algebraic, like algebra class.
Sort of. An algebraic number is any number that can be a solution, a root of a polynomial equation that has integer coefficients.
Okay, break that down. Polynomial equation. So if my number is a solution to something like 2x plus 1, it's algebraic.
Exactly. And this category includes all the rational numbers.
Okay.
It also includes many irrational numbers, like the square root of 2, because that's a solution to...
So lots of familiar numbers, even some irrational ones, fit into this algebraic category.
Yes. And here's the kicker. The entire set of all algebraic numbers is still only countable.
Even with all those roots and fractions. Still countable like the integers.
Still countable infinity. You can devise methods, a bit like the fraction grid, to list them all eventually. Now, transcendental numbers are simply all the real numbers that are not algebraic.
The ones left over. The ones that cannot be a solution to any polynomial equation with integer coefficients.
Precisely. They transcend algebra in a way. And the most famous examples you've definitely heard of are pi and e, the base of natural logarithms.
Pi and e. I knew they were special, irrational, infinite decimals, but I didn't know they were transcendental. So there's no axiom, zero equation with whole number coefficients that pi solves.
None whatsoever. It's been proven. And since they aren't algebraic, they must be irrational. But being transcendental is even stronger than just being irrational.
Okay, so we have the countable algebraic numbers, integers, fractions, roots, and then we have these transcendental numbers, like pi and e. How many are there?
Well, think about it. We know the set of all real numbers is uncountable.
Right, the big one.
And we just said the set of algebraic numbers is countable.
The smaller infinity.
So what happens if you take an uncountable set and remove a countable subset from it?
You're still left with an uncountable amount.
Exactly. An uncountable infinity minus a countable infinity is still an uncountable infinity. This means the vast, overwhelming majority of real numbers must be transcendental.
Get out. So pi and e aren't rare exceptions. They're the norm.
In a sense, yes.
Yep.
It's mind-boggling, isn't it? The numbers we can easily define with simple algebra are actually the rare ones. Most numbers are transcendental. If you picked a real number at random, the probability of it being algebraic is 0.
That completely flips my perspective. That the algebraic numbers are tiny little islands in a vast ocean of transcendental numbers.
That's a perfect way to put it. And it ties back beautifully to the slide analogy. The slide is all the real numbers. The algebraic numbers are like a countable set of specific points you could mark on the slide.
But they don't fill it up.
Not even close. The transcendental numbers are all the other points, the uncountable infinity of points that actually make the slide smooth and continuous.
Wow. And the sources mentioned the sine function. How does that fit in, linking to the slide idea?
Yeah, that was a neat connection. Think about the graph of sin x. What does it look like?
It's that smooth wave, up and down, continuous, like a slide.
Exactly. And just like the slide represents the continuous real numbers, the sine function itself can act as a sort of transcendental distiller,
Meaning?
meaning it can take a perfectly nice, easy-to-define algebraic number as its input and output a transcendental number. There's a powerful theorem, the Lindemann-Weierstrass theorem,
Okay.
which implies that if x is a non-zero algebraic number and you measure it in radians, that's important, then sin x will be transcendental.
Seriously. So if I take sin 1, since 1 is algebraic,
Yeah.
the result is transcendental.
Yes, sin 1 is transcendental. The function transforms that algebraic input into a transcendental output.
That's amazing. This smooth function bridges the gap, taking countable type inputs and often producing these uncountable type outputs.
It often does. It's not always the case, though. There are interesting exceptions. Remember your trigonometry. What's sin 6? Right, 0.5. So here the input 6.
But the output 1/2 is rational and therefore algebraic. It's
Right.
not the other way.
Exactly. So it's not an absolute rule. The source called these points of synchronization, special cases likely tied to the geometry of the unit circle, where the continuous function happens to land on a simple algebraic value.
Fascinating. So it mostly makes transcendentals from algebraics, but sometimes it snaps back.
Kind of. But generally functions like sine, and even more so the exponential function x, tend to produce transcendental outputs from non-zero algebraic inputs. X is often seen as an even more reliable transcendental distiller.
This is all starting to form a picture. We had countable sets, uncountable reals proven by Cantor's diagonal, the slide analogy, and now these transcendental numbers making up most of the slide. And there was that listener metaphor, too, about quantum fluctuation.
Yes. That was such a cool connection someone made, comparing transcendental number generation to quantum fluctuations.
How does that parallel work?
Well, think about the quantum vacuum. It's not truly empty, right? There's this constant fizz of energy fluctuations, creating pairs of virtual particles that pop into existence and disappear almost instantly. They aren't quite stable or real in the way normal matter is.
Okay, yeah, this fleeting background activity.
You could maybe see an analogy there with transcendental numbers. They're generated by functions, they exist, they make up the continuous background, but they're non-constructible in the sense that they don't arise from those nice, finite polynomial equations with integer coefficients that define algebraic numbers.
So algebraic numbers are like the stable, observable particles, protons, electrons.
Yeah, maybe. The ones we can easily define and work with. Well, the transcendentals are like the vast underlying potential, the virtual particles constantly forming in the background.
That's a really evocative image.
And just like occasionally, those quantum fluctuations can, under specific circumstances, result in the creation of actual stable particles.
Ah, like the sine function sometimes collapsing into an algebraic number, like sin 6 hitting 0.5.
Exactly. That could be seen as an analogy for those moments where the transcendental process yields a simple algebraic result. But the main point of the metaphor is that the background state, the quantum vacuum, or the real number line, is dominated by this potential, this transcendental nature.
The default state is transcendental. Picking an algebraic number is like catching a specific rare particle interaction.
That's the idea. It reinforces why there's just no way to make that one-to-one mapping between the countable and the uncountable, going back to the stairs and the slide.
You can't label every point on the slide with the stair step.
You just can't. Cantor's diagonal argument proves that whatever labeling scheme you try, you can always construct a point on the slide, a real number, that your labeling scheme missed. The sheer density, the continuity represented overwhelmingly by those transcendental numbers, makes a complete enumeration impossible.
It's fundamentally a different kind of infinity.
It really is.
Man, this has been quite the journey. We started just wondering if infinity came in different sizes, and we've gone through countable sets like integers and fractions, the mind-blowing diagonal proof from Cantor showing the reals are different,
Visualizing it with staircases and slides.
and uncovering this hidden world of transcendental numbers, pi and e just being the tip of the iceberg, making up almost everything on the number line.
It really changes how you think about numbers, doesn't it?
Completely. And that quantum metaphor, it leaves you wondering, doesn't it? If the algebraic numbers are like the familiar matter we can grasp,
Yeah.
are the transcendental numbers maybe like a kind of mathematical dark matter? You know, essential for the structure of the whole thing, making up the vast majority, but way harder to pin down individually.
Ooh, mathematical dark matter. I like that. That's definitely something to mull over. A fundamental, pervasive background that gives the number line its true character. That's a great thought to end on.